Hi, good afternoon, everyone. My name is Apoorv Tandon. I'm an undergraduate student at the Computer Science Department of IIT Kanpur. And today we're back with the second lecture of the chapter Continuity and Differentiability, which you would remember is the second chapter in calculus throughout our JEE journey. And the chapter before this in calculus was limits and derivatives, wherein we studied the definition of limits, various methods to evaluate limits, and also what the meaning of differentiability is, and how we can verify through the concept of limits whether a function is differentiable at a point. So this was all the first chapter of calculus. We've also covered one lecture of this chapter. So in that lecture, we discussed what exactly continuity means. We gathered a basic intuition for continuity कि ग्राफ पे पेन को बिना उठाए ड्रॉ कर पाए किसी फंक्शन के ग्राफ को, तो उसे कंटिन्यूअस कहते हैं उस पॉइंट पर। तो हमने ये इंट्यूशन गैदर की कंटिन्यूटी की और उसकी रिगरस मैथमेटिकल डेफिनेशन देखी लिमिट्स के दौरान, और उसके बाद कंटिन्यूटी को अप्लाई करने की कुछ प्रॉपर्टीज भी देखी। एंड वी एंडेड द फर्स्ट लेक्चर विद डायरेक्शनल कंटिन्यूटी, और मैंने कहा था कि हम डायरेक्शनल कंटिन्यूटी को एक कॉन्सेप्ट कंटिन्यूटी ऑन एन इंटरवल में अप्लाई करेंगे। So first, let's look at a few examples just to start off this session. Um, Based on the first lecture, जो हमने पिछले लेक्चर में कवर किया था, उसे अप्लाई करते हुए कुछ एग्जाम्पल देख लेते हैं। So पहला एग्जाम्पल, what type of discontinuity does the function f of x equals 1 upon the natural logarithm of the modulus of the difference between x square and 4 have? अब इस क्वेश्चन को सॉल्व करने के लिए इस क्वेश्चन में हमें ये पूछा गया कि ये दिया गया है कि ये फंक्शन कहीं तो डिसकंटिन्यूअस है। अब हमें ये ढूंढना है कि पहले तो ये कहाँ डिसकंटिन्यूअस है, और जहां वो डिसकंटिन्यूअस है वो किस डेफिनेशन से डिसकंटिन्यूअस है। मतलब आपको डिसकंटिन्यूटी का फ्लो चार्ट याद होगा। डिसकंटिन्यूटी के वेरियस टाइप्स होते हैं, रिमूवेबल, नॉन रिमूवेबल, और हर एक में फर्दर क्लासिफिकेशन होती है ताकि टोटल टाइप्स ऑफ डिफरेंशिएबिलिटी डिसकंटिन्यूटी 5 होते हैं। तो उन पांचों में से इस फंक्शन में जहां ये डिसकंटिन्यूअस है उस पॉइंट पर कौन सी टाइप की डिसकंटिन्यूटी है, ये पूछा गया है। तो क्लियरली अगर ये फंक्शन डिफाइन हो रहा है, तो जो लॉगरिथम का आर्ग्यूमेंट है, मतलब डिनोमिनेटर शुड बी नॉन जीरो फॉर एनी रैशनल फंक्शन। सो जो इसका आर्ग्यूमेंट है लॉगरिथम का, इट शुड नॉट बी इक्वल टू 1, है ना। अगर ये 1 हो जाता तो लॉगरिथम ऑफ 1 इज 0 एंड 1 अपॉन 0 इज अनडिफाइंड, so it would have discontinuity at the point x is equal to 4, x square is equal to 4, x square minus 4 is equal to 1. So we have to ensure that the absolute value of x square minus 4 is not 1. इसे सॉल्व करने के लिए हम मॉड्यूलस खोलेंगे। एक तरफ हम लिखेंगे x square minus 4 is equal to 1। यहाँ पे नॉट इक्वल टू 1 के लिए पहले हम ढूंढेंगे कौन से वैल्यूज ऑफ x के लिए ये 1 हो रहा है, और उन्हें हम निगेट कर देंगे। तो first x square minus 4 is equal to 1, secondly x square minus 4 is equal to minus 1. In this case x square should be less than 4, right? So आप इन सब को solve करेंगे, then you will get 4 values of x which are plus minus root 3 and plus minus root 5. Also logarithm is not defined for 0. आपको log का ग्राफ याद होगा, it goes something like this. At 0 it extends to negative infinity infinitely, indefinitely, मतलब ये इसका कोई 0 पर वैल्यू नहीं है। So one condition is that the argument should not be 1, so that denominator is non-zero. Secondly, the argument should not be 0 either, because that is out of the domain of logarithm. So in case x square minus 4 was 0, x would be plus minus 2. So we have total 6 possible candidates for discontinuity of this function, which we will now verify. First we will look at the second case. इस केस में आप देख सकते हैं, भले ही ये फंक्शन डिफाइन ना हो रहा हो, पर इसकी लिमिट तो हम डिफाइन कर ही सकते हैं। नाउ द लिमिट as x tends to plus or minus 2 doesn't matter. 1 upon the natural log of modulus x square minus 4. Clearly, the natural log of x square minus 4 as x tends to 2 or minus 2 will tend to negative infinity, right? Because इसकी आर्ग्यूमेंट जीरो की तरफ बढ़ती जा रही है, लॉगरिथम माइनस इन्फिनिटी की तरफ बढ़ता जाएगा, एंड लिमिट ऑफ 1 अपॉन प्लस और माइनस इन्फिनिटी इज जीरो. सो इसकी लिमिट एग्जिस्ट करती है और वो जीरो है, मगर ये फंक्शन 2 पे एग्जिस्ट नहीं करता, प्लस माइनस 2 पे एग्जिस्ट नहीं करता. और आपको याद होगा जब लिमिट एग्जिस्ट करता है LHL इज इक्वल टू RHL, पर f of a does not exist, then what is it called? It's called a removable missing point discontinuity, है ना? तो पॉइंट्स x प्लस माइनस 2 पे we have a missing point discontinuity. Now we will check for x equal to plus minus root 3 and x equal to plus minus root 5. क्लियरली आप देख सकते हैं कि यहाँ पे भी हमें पहले तो लिमिट कैलकुलेट करना पड़ेगा. ऑब्वियसली f of x does not exist for these both values, क्योंकि हमारे कंडीशन I इस हिसाब से कि ये सारे x के वैल्यू डोमेन के बाहर है, मतलब इवन हियर f of x तो does not exist. पर उसके अलावा हमें ये भी देखना है कि टाइप ऑफ डिसकंटिन्यूटी कौन सी है, रिमूवेबल है कि नॉन रिमूवेबल है, और उसके लिए जरूरी है कि हमें पता होना चाहिए लिमिट एग्जिस्ट करता है कि नहीं. तो in this case we will try for one value of x out of these four, which is root 3. The limit as x tends to root 3 of f of x. इस फंक्शन को मैं f of x बुला रहा हूँ. So the limit as x tends to root 3 of f of x. Direct substitution से try करें हम, so it comes as 1 by natural log of 1. And the natural log of 1 is 0, so this limit tends to infinity. Right? So this limit tends to infinity. आपको याद होगा जब भी किसी भी लिमिट की वैल्यू एटलीस्ट वन ऑफ द लेफ्ट हैंड और द राइट हैंड लिमिट टेंड्स टू प्लस और नेगेटिव इन्फिनिटी, we call it a non-removable infinite type or asymptotic type discontinuity. So that is what it is in this case. Always keep in mind, याद रखिएगा कि अगर किसी फंक्शन में आपको दिख रहा है कि ना ही लिमिट एग्जिस्ट करता है और ना ही फंक्शन की वैल्यू है, तो आपको याद रहना चाहिए कि the non-removable discontinuity is the broader classification. You cannot call this a removable discontinuity because f of x does not exist at root 3, because the limit does not exist either. So the non-existence of limit always trumps the non-existence of f of x or the isolation of f of x. तो जैसे इस केस में मिसिंग पॉइंट तो था ही, पर उसके अलावा लिमिट भी एग्जिस्ट नहीं कर रहा था, लिमिट इंफिनिटी की तरफ जा रहा था. We will call this a non-removable infinite type या asymptotic type discontinuity, ना कि removable missing point. You understand? Because non-removable discontinuity is a more superior classification. And when limit does not exist, whatever you do to f of x, the function cannot be made continuous at the point. इसलिए ये non-removable infinite type discontinuity कहलाएगा. So that was the first example I wanted to show. The same will be the case for negative root 3 plus minus root 5, as it was for positive root 3. Now let's move on to our first concept for the second lecture, which is continuity on an interval. जो आपको याद होगा डायरेक्शनल कंटिन्यूटी की एप्लीकेशन है. So let's write that down. Continuity on an interval. आपको 11th स्टैंडर्ड के पहले चैप्टर से याद होगा व्हाट एन इंटरवल इज. इन द चैप्टर ऑफ सेट्स वी डिस्कस कि रियल नंबर लाइन पे एक इंटरवल क्या होता है, और आपको ये भी याद होगा कि इंटरवल्स के डिफरेंट टाइप्स होते हैं. तो इस सब टॉपिक को हम उन्हीं टाइप्स में डिस्कस करेंगे. सो पहला टाइप होता है ओपन इंटरवल. तो ओपन इंटरवल, अ फंक्शन इज सेड टू बी कंटिन्यूअस ऑन एन ओपन इंटरवल. मान लीजिए a कॉमा b है ओपन इंटरवल. इफ f of x is continuous for all x belonging to this open interval and no additional condition हो. So अगर x a और b के बीच excluding a and b हर पॉइंट पर continuous है, then f of x is said to be continuous on the entire open interval. So mathematically लिखें, for all c belonging to a comma b the limit as x tends to c of f of x is equal to f of c. That is the meaning of continuity on an open interval. Let's look at an example for this. Greatest integer function. आपको greatest integer function के ग्राफ से याद होगा जो कुछ ऐसा दिखता है. From 0 to 1 it assumes the value 0. From 1 to 2 assumes the value 1 and so on. So अब मैं कह रहा हूँ कि ओपन इंटरवल 1,2 में नॉट इंक्लूडिंग 1 और 2. अब देख सकते हैं अगर 2 और 1 को मैं एक्सक्लूड कर दूं तो इस फंक्शन में कोई गैप्स नहीं आ रहे. मतलब इस पूरे ग्राफ को हम बिना पेन उठाए बना सकते हैं, which means it is continuous on the open interval because it is continuous at all x belonging to 1,2. 1 और 2 के बीच में हर पॉइंट पर ये कंटिन्यूस है, इसलिए ये पूरे ओपन इंटरवल में कंटिन्यूस है. So greatest integer function is continuous on the entire interval, open interval 1,2. However, अगर हम इसी फंक्शन के लिए ओपन इंटरवल 1,3 लेंगे, डेफिनेशंस को देखिए, it should be continuous at all points between the end points of an open interval, not excluding the end points, not including the end points. So 1,3 के बीच 2 भी आता है. एंड आपको याद होगा ग्रेटेस्ट इंटीजर फंक्शन इज ऑलवेज डिसकंटिन्यूअस एट एनी इंटीग्रल पॉइंट. व्हाई? क्योंकि इंटीग्रल पॉइंट के आगे और पीछे फंक्शन की वैल्यू चेंज हो जाती है, तो लेफ्ट साइड और राइट साइड वाले लिमिट्स इक्वल नहीं हो सकते. इसलिए द ग्रेटेस्ट इंटीजर फंक्शन is not continuous on the open interval 1,3 because it is discontinuous at x is equal to 2. It's not continuous at x equal to 2, and in fact it has a non-removable jump discontinuity at x is equal to 2, right? So now we will discuss continuity on a closed interval. और इन्हीं दो concepts को merge करके you can also see continuity for a half open, half closed interval. So closed interval. Condition लिख लेते हैं. A function f of x is said to be continuous on a closed interval a comma b if इसमें 3 कंडीशंस होते हैं. इट इज कंटिन्यूअस फॉर ऑल x belonging to open interval a comma b, right? So this is the condition for continuity on the open interval a comma b. In addition to continuity on open interval a comma b, there will be 2 additional conditions which will ensure continuity on this closed interval. क्लोज्ड इंटरवल की कंटिन्यूटी के लिए इस कंडीशन के अलावा 2 और कंडीशंस हैं जो काफी इंपॉर्टेंट है, वो हम लिखेंगे. And this is where we will apply the concept of directional continuity as well. It must be right continuous at x is equal to a. That is, mathematically, the limit as x tends to the right neighborhood of a must be equal to f of a. So in this case, at the left end point of a closed interval, we do not require the evaluation of the left-hand limit. We must only ensure right continuity at the left end point, at the lower end point of the closed interval. इसका analogy होगा third condition, आप guess कर सकते हैं. It is left continuous at x equals to b, the right end point of the closed interval. Mathematically, the limit as x tends to the left neighborhood of a of f of x must be equal to f of b. And in this case, right end point पर right hand limit की evaluation जरूरी नहीं है. So these are the conditions for continuity on a closed interval. For example, वही example ले लेते हैं greatest integer function का on the closed interval 1,2. 1,2 closed interval पे अगर हम इस function के graph plot करें, again 0 से 1 तक, but excluding 1, it takes on the value 0, and from 1 excluding 2, it takes the value 1. So the greatest integer function की हमें 1,2 closed interval पे continuity देखनी है. ओपन इंटरवल वाले एग्जांपल से याद होगा कि ओपन इंटरवल 1,2 में तो ये कंटिन्यूअस है, तो पहला कंडीशन सेटिस्फाई होता है। सेकंड कंडीशन, इट इज राइट कंटिन्यूअस एट द लेफ्ट एंड पॉइंट। लेफ्ट एंड पॉइंट एफ ऑफ 1 है, 1 है, x इक्वल्स टू 1, f of 1 is 1, which is also equal to the right hand limit, so it is right continuous at the left hand point, so that condition is satisfied as well. Now we must look at the next condition, which is x equals to 2. F of 2 is equal to 2. However, it is not equal to the left hand limit at x equals 2. Why? Because this is clearly 1, which is why the third condition is not satisfied. The left continuity at the right endpoint of the closed interval is not satisfied, and therefore the greatest integer function is not continuous on the closed interval 1, 2. तो इन एग्जाम्पल से एक नोट लिख लीजिए, एक ऑब्जर्वेशन। इफ अ फंक्शन इज कंटिन्यूअस ऑन ए क्लोज्ड इंटरवल a, b, देन इट इज बाउंडेड। मतलब हम ऐसे दो रियल नंबर ढूंढ सकते हैं जिनके बीच ही एफ ऑफ एक्स की सारे वैल्यूज होंगी। एफ ऑफ एक्स डज नॉट एस्केप a certain upper limit and does not go below a certain lower limit. हम f of x की exact range ढूंढ सकते हैं। So if a function is continuous on a closed interval a, b, then it is bounded, which means a continuous function whose domain is a closed interval has its range also in a closed interval. So ये continuity का काफी important application है कि अगर हमें पता है किसी फंक्शन की डोमेन एक पर्टिकुलर क्लोज्ड इंटरवल है, तो उसकी रेंज भी एक पर्टिकुलर क्लोज्ड इंटरवल है। मतलब द फंक्शन कैन नॉट सडनली एस्केप टू इन्फिनिटी और नेगेटिव इन्फिनिटी। अगर उसका डोमेन क्लोज्ड है और वो उस डोमेन पे कंटिन्यूअस है, तो हम ये कंक्लूड कर सकते हैं कि उसके रेंज में एक मैक्सिमम नंबर और एक मिनिमम फाइनाइट नंबर होंगे, उन दोनों नंबर के बीच ही ये फंक्शन कन्फाइन रहेगा। सो दैट इज द कॉन्सेप्ट इन दिस नोट। इन कॉन्सेप्ट्स पे एक एग्जांपल देखते हैं। फाइंड द पॉइंट्स ऑफ डिसकंटिन्यूटी। मैंने इन डोमेन मेंशन नहीं किया है, तो वी मस्ट अज्यूम इट इज ओवर द सेट ऑफ ऑल रियल नंबर्स आर of the following functions. So the first function is f of x is equal to 1 over 2 times sin x minus 1. एक प्रॉपर्टी होती है कंटिन्यूअस फंक्शंस की कि एक नोट भी था कि all trigonometric, rational, algebraic, polynomial, etc. functions are continuous over their domain. This is a rational trigonometric function. Why? Because not only is the trigonometric function 2 sin x minus 1 continuous, but its inverse is also continuous because that is the rational trigonometric function. पहले तो trigonometric function है डिनोमिनेटर में, और क्योंकि वो डिनोमिनेटर है, पूरा फंक्शन एक रैशनल फंक्शन है। So all rational functions are continuous over their domains, and trigonometric functions are also continuous over the domain. So rational trigonometric functions are also continuous over their domains. This is a property of composite functions. F of g of x is continuous at a particular point as long as g of x is continuous, and f of x is continuous over all values that g of x takes. So f of x equals 1 by 2 sin x minus 1. हमारी only suspicion for discontinuity is where f of x does not exist. And clearly that point exists, है ना? f of x does not exist where? Where 2 sin x minus 1 is equal to 0. अगर denominator 0 हो जाए, तो f of x is not defined. Sin x is equal to 1 over 2 पे discontinuity हो सकती है. And trigonometry से याद होगा, इसका most general solution is n pi plus negative 1 power n of pi over 6. क्योंकि इसका पर्टिकुलर सोल्यूशन 30 डिग्रीज पाई ओवर 6 है, इसका जनरल सोल्यूशन इज n pi plus negative 1 to the power n pi over 6 where n is any integer. तो इस हर पॉइंट पर f of x does not exist, एंड इस इनके आगे पीछे पॉइंट्स पर लिमिट इक्वल नहीं होंगे। ये वेरीफाई किया जा सकता है कि पाई ओवर 6 के आगे वाले पॉइंट्स पर sin x 2 sin x minus 1 पॉजिटिव होगा एंड इट विल टेंड टू पॉजिटिव इन्फिनिटी, whereas पाई ओवर 6 के पहले पॉइंट्स पर हम मान लो 29.99999 डिग्रीज में डिनोमिनेटर जीरो के बहुत करीब होगा पर नेगेटिव होगा, तो f of x will tend to negative infinity. Therefore, um, this has we can be misled to think कि this function has a removable मिसिंग पॉइंट डिसकंटिन्यूटी, क्योंकि एफ ऑफ एक्स यहाँ डिफाइन नहीं है। पर आपको याद होगा नॉन रिमूवेबल डिसकंटिन्यूटीज ट्रम्प ओवर रिमूवेबल डिसकंटिन्यूटीज। अगर हमें दिख गया कि लिमिट एग्जिस्ट नहीं कर रहा है, तो भले ही फंक्शन एग्जिस्ट ना करे, हम उसे नॉन रिमूवेबल कहेंगे, क्योंकि फंक्शन की वैल्यू चेंज करके हम इसे कंटिन्यूस नहीं बना सकते। इसलिए दिस इज अ नॉन रिमूवेबल इनफाइनाइट टाइप या एसिम्प्टोटिक डिसकंटिन्यूटी। इसका एक और एग्जांपल देख लेते हैं। या f of x is equal to 1 over x to the 4 plus x square plus 1. Now the only possible discontinuity here can arise from the zero value of the denominator, क्योंकि ये भी rational algebraic function है। The denominator is algebraic, it's a polynomial function, and this is a rational function with the denominator as a polynomial function. So this is continuous over its entire domain, and let's find the domain. Prove किया जा सकता है कि denominator is always non-zero. Basically, this function does not have any real roots. This is from quadratic equations. X square को y मान लीजिए and y square plus y minus 1 अब plus 1 आप देखेंगे discriminant is negative, so roots don't exist. So this function basically has its domain as real number, and a polynomial function or rational function is continuous over its entire domain. Therefore, f of x is continuous over its entire domain, which is the set of all real numbers. So it does not have any point of discontinuity. Now, discontinuity continuous functions के कुछ algebraic properties होती हैं कि लो functions अगर continuous है, discontinuous है, तो उनके sum product difference quotient की continuity के बारे में क्या conclude किया जा सकता है. So we will list whatever properties are self-evident without any additional condition right now. So algebraic operations on two functions. Pehla conclusion, if f and g, which are two functions, f of x and g of x, are continuous in a given interval, open or closed, then their sum product difference or quotient is also continuous in that same interval. इसमें बस एक एडिशनल कंडीशन आता है कोशेंट के लिए, डिनोमिनेटर बी नॉन जीरो, क्योंकि वो डोमेन के बाहर आ जाएगा अगर डिनोमिनेटर जीरो है तो। एंड आपको ये तो रूल पता ही था कि any rational function is continuous over its entire domain. So this rule is an analogy to that. It is another way of saying that same rule कि sum product difference quotients are continuous except when the domain of the function changes. The domain will change when the denominator is zero. So for quotient, we must ensure that the denominator is non-zero. Secondly, if f of x is continuous, but g of x is discontinuous at a point x equals to a, f plus minus g of x, the function f plus minus g is discontinuous at that point. इसके proof के लिए, suppose f of x is continuous at x is equal to a, which means that the limit as x tends to a, f of x is equal to f of a. However, the discontinuity of g of x at x equals to a implies that the limit as x tends to a of g of x is not equal to g of a. Applying the property of limits, the limit as x tends to a of the sum of both functions is in fact the limit as x tends to a of this. It is the sum of the limits of the two functions. And ये पहला लिमिट f of a है इससे, और दूसरा लिमिट इज नॉट इक्वल टू g of a. सो मान लीजिए इट इज g of a प्लस सम रियल नंबर के, मतलब excluding zero, basically saying that it is distinct from g of a इस conclusion से. So we can conclude that the limit of f plus g is unequal to the limit of f is unequal to the value of f plus g at x equals to a, which means that the limit of f plus g or f minus g is discontinuous at x equals to a. The similar procedure can be applied for the difference of the two functions. All right. So the third property, if f of x is continuous, but g of x again is discontinuous. G of x is discontinuous at the same point x equals a. Nothing can be concluded about the product of quotient. Nothing can be concluded about the continuity of the product of quotient functions at x equals a. So to justify this to ourselves, let's take an example. Let's define f of x to be the identity function x and g of x to be the greatest integer function. First, let's check the continuity at x equals 0. F of x is, of course, a polynomial function with which is linear in one variable. So f of x is, of course, continuous over its entire domain, which is the set of all reals. So f of x is continuous at x equals 0. However, g of x is discontinuous at all integer points. So g of x is discontinuous at x equals 0. Now we must check the continuity of the product function fg defined as x greatest integer x at x equals 0. Now इसकी value 0 ले लें. The fg value at x equals 0 is 0. So fg of x equals 0, right? Now we must check the limit as x tends to 0 of fg of x. And आप देख सकते हैं ग्रेटेस्ट इंटीजर फंक्शन की जो भी वैल्यू हो डायरेक्ट सब्स्टिट्यूशन से बाहर वाले x की वजह से इस लिमिट की वैल्यू 0 है. Clearly the two coincide. The limit is equal to the value of the function at the point. So fg is continuous at x equals 0, right? It has trumped over the discontinuity being created by the greatest integer function. The presence of x being multiplied with the greatest integer function has made this function fg continuous at x equals 0. तो भले ही f continuous था, g discontinuous था, पर fg continuous मिल गया. आप देखेंगे कि ये रूल नहीं है कि हमेशा continuous मिलेगा. For example, x equals 1 पे f of course is continuous over the entire set of reals. G is discontinuous at all integral points. Now fg defined as x times greatest integer of x, um, fg of 1 is equal to 1, right? Greatest integer of 1 is 1 and x equals 1 pe y is equal to x is 1. So fg of 1 is exactly 1. We must now check the left hand and the right hand limits of fg. Left hand limit पे हम x tends to 1 minus limit x tends to 1 minus of x greatest integer of x. 1 minus पे greatest integer 0 होता है, exactly 0 होता है. 1 से छोटे किसी भी पॉइंट पर 0 से बड़े, तो x की जो भी वैल्यू हो इस पूरे लिमिट की वैल्यू 0 होगी. राइट हैंड लिमिट पे लिमिट x tends to 1 plus x greatest integer of x. ग्रेटेस्ट इंटीजर ऑफ x की वैल्यू 1 से बड़े किसी भी पॉइंट पर 2 से छोटे पॉइंट पर 1 होती है और x की डायरेक्ट सब्स्टिट्यूशन से 1 आएगी. So the right hand limit is 1. Clearly the limit does not exist and this has the non-removable jump type discontinuity, right? So हमने देखा एक ही प्रोडक्ट फंक्शन में सेम ही कंडीशंस में जहां f कंटिन्यूस है g डिसकंटिन्यूस है, f कंटिन्यूस है g डिसकंटिन्यूस है, x इक्वल टू 0 पे कंटिन्यूस आ रहा है, x equals 1 पे discontinuous आ रहा है, wherein we conclude that no conclusion can be made about fg or f over g when we are given the continuity of f and g, right? So ये याद रखिएगा. इन एग्जांपल्स से एक corollary हम डिड्यूस कर सकते हैं and let's write that down as a note, right? Number one, if f of x is um, discontinuous at x equals a and g of x is continuous at x equals a with g of a equals 0, right? Then the product function defined as h of x is continuous at x equals a. जैसे हमने देखा था x equal to 0 पे x times greatest integer of x was continuous because x was evaluating to exactly 0 and it neutralized any discontinuity caused by the greatest integer of x. Similarly, if we have the product of any two functions where one of the function becomes 0 at the point where we are checking continuity, then the entire product function will be continuous, right? So that is the note. Lastly, yeah. So the last subheading, last point under algebraic operations of continuous and discontinuous functions. If both f of x and g of x are discontinuous, for example, at the same point x equals a, any algebraic operation, any algebraic combination of f of x and g of x may or may not be continuous, means nothing can be concluded. If it is given that both f and g are discontinuous at x equals a, we cannot conclude anything about f plus g, f minus g, f g, or f over g. So it will be useful to keep these 4 points and this note in mind. Let's look at an example using the concept of algebraic operations on continuous and discontinuous functions. So the question is, prove that the function f of x, which is defined as the greatest integer of x times cosine of 2x minus 1 pi by 2. In this question, it is given that square brackets imply the greatest integer function is continuous for all reals. Right? Now solution. Clearly, cosine of 2x minus 1 pi by 2 is continuous over its entire domain, which is the set of real numbers. So we need not check that. Let's take the cosine part of this function as, say, h of x, and the greatest integer part as g of x. I am not going to check this function for open intervals between two integers, because both g of x and h of x are continuous on that interval. So their product function is also continuous by the first conclusion in algebraic operation. However, I will check all integral points where g of x becomes discontinuous, but h of x remains continuous, right? And by the third point, when h of x is continuous, g of x is discontinuous, we cannot directly conclude anything about the product function. So we must check for all integers. मान लीजिए हम कोई भी integer k ले लें, where k is an integer. Let k be some integer. Clearly, g of x is discontinuous at k. However, ये प्रोडक्ट फंक्शन फिर भी कंटिन्यूस हो सकता है इस नोट की वजह से. और इस नोट में क्या लिखा था हमने? When the function which is continuous becomes zero at points where the counterpart function is discontinuous, then the entire product function is continuous at that point. So हर इंटीजर के पॉइंट पर g of x डिसकंटिन्यूस है. However, हम h of x के वैल्यू देखेंगे. अब देखेंगे हर इंटीजर पॉइंट पर 2x minus 1 becomes an odd integer, and odd integral multiples of pi over 2 make the cosine 0, right? H of x is satisfying the condition in this note. H of x is becoming 0 wherever g of x is discontinuous. Therefore, f of x is continuous at all these integral points because h of x becomes 0 at all integral points. And we already know that f of x is continuous for all points between two integers, which means it is continuous for all integral and non-integral points. Basically, f of x is continuous for all reals. So now we're going to look at the continuity of some specific functions. All right. So the first subheading that we'll look at under this topic is functions involving the greatest integer function. इसके कुछ एग्जांपल हमने ऑलरेडी देख लिया है. So let us look at it in more detail. So basically, f of x equals greatest integer of x is discontinuous at all integral x. इसी के composite extension पे अगर f of g of x दिया गया हो as the greatest integer of g of x, it will be discontinuous at all integral g of x. That is, it is discontinuous for all x such that g of x becomes an integer, right? And so on. f of g of h of x के लिए भी यही condition extend होता जाएगा. So so the greatest integer function में हमें integral functions पर continuity check करना याद रहना चाहिए. इसे एक और तरीके कहने का एक और वे से कहने का तरीका है कि अगर बेसिकली f of g of x is not continuous. जब हम continuous बोलते हैं we mean over its entire domain. Is not continuous if g of x y is equal to g of x crosses y equals k for any k belonging to integers. Basically, this is saying that if g of x ever becomes an integer, f of g of x is not continuous. However, इसमें एक caution की बात है, इसकी एक exception है, unless g of x equals to k at its turning point. अगर ग्राफ उसी इंटीग्रल पॉइंट पर टर्न ले रहा है, it may be continuous. जरूरी नहीं है कंटिन्यूस हो, पर इसे हम ध्यान से देखना होगा इस केस में कि g of x at x equals to k is its turning point. इसको देखने के लिए डेमोन्स्ट्रेट करने के लिए एग्जांपल देख लेते हैं. सपोज वी डिफाइन द ग्रेटेस्ट इंटीजर ऑफ sin x. sin x का ग्राफ प्लॉट करते हैं, राइट? सो बिटवीन negative pi and pi sin x looks something like this, right? So 0 pi negative pi. हमें देखनी है कंटिन्यूटी एट पाई ओवर टू, जहाँ पे sin x becomes an integer, and minus pi over 2, or let's say 3 pi over 2, जहाँ पे sin x becomes negative 1, right? So first let's look at x equals pi over 2. As x tends to pi over 2, sin x is never exactly equal to 1, and graph से देख सकते हैं is always less than 1. The limit, both limits, in fact, are 0. However, the function is 1, which means it is discontinuous at x equals pi over 2. However, at x equals 3 pi over 2 or negative pi over 2, we see that the left hand limit and the right hand limit, they are both negative and greater than minus 1. So the greatest integer is negative 1. Left hand and right hand limit are negative 1. And f of 3 pi over 2 is also negative 1. Sine of 3 pi over 2 is negative 1. So the limit and the value of the function coincide. Therefore, it is continuous at x equals to 3 pi over 2. So we saw that where the greatest integer function's argument is attaining integer points, it may or may not be continuous at turning points. X equals pi over 2 and x equals 3 pi over 2 were turning points for sin x. वहां पे उसकी इसका स्लोप चेंज हो जाता है. तो x equals pi over 2 में हमने देखा डिसकंटिन्यूटी आ रही है. However, x equals 3 pi over 2 में कंटिन्यूटी आ रही है. So it is important to check carefully for those integral points where sin x is turning. Turning points पे ध्यान से देखना जरूरी होता है ग्रेटेस्ट इंटीजर फंक्शन के केसेस में. टर्निंग पॉइंट के केस के अलावा when g of x attains integer points, the greatest integer function is discontinuous. So second case of particular functions involving the signum function. Signum function की definition याद कीजिए. If f of x is defined as the signum of x, it will be equal to -1 when x is negative, 0 when x is 0, and +1 when x is positive. If I extend this definition to f of g of x, which is the signum of g of x, it will be -1 for all x such that g of x is less than 0, 0 for all x such that g of x is equal to 0, and 1 for all x such that g of x is positive, right? So f of g of x will be discontinuous because the signum of x function is clearly discontinuous at x equals 0, right? Because left hand limit -1, right hand limit 1, and functional value is 0. it has the jump type in non-removable discontinuity. So f of g of x will be discontinuous for all x such that g of x is 0. At all roots of g of x, the signum g of x is discontinuous. Alright, let's look at an example for the application of this concept. मान लीजिए आपको दिया गया हो एक फंक्शन f of x defined as the modulus of x times signum x cube minus x, right? Clearly, mod x is a continuous function over its entire domain, which is reals. Now, signum of x may or may not be continuous. We will check for all points where it is discontinuous, because wherever it is continuous, the product of two continuous functions is continuous, right? So now we will look at where all signum x is discontinuous. And इस रूल से हमें signum of x के लिए argument के roots देखने हैं. Where x cube minus x becomes 0, signum of x will be, signum of g of x will be discontinuous. इसके दो रूट्स हैं, x equals 0 and 1. x equals to 0 पे हम ऑब्जर्व करेंगे कि mod x भी 0 बन जा रहा है. एंड हमारे नोट से when g of x into h of x, where g of x is continuous, h of x is discontinuous, but g of x becomes 0 at the point where we are checking continuity, the product becomes continuous, right? So f of x is continuous at x equals 0, but it is discontinuous at x equals 1 because mod x is not becoming 0 at x equals 1, right? So that is what we can conclude in this example. This is the only point of discontinuity of f of x, and it is caused, it arises because one of the two functions in the product is discontinuous and the other one is not becoming 0. All right. So the next subheading under this topic of specific functions is function involving infinite limit. इन क्वेश्चंस के लिए एक बेसिक कॉन्सेप्ट होता है which we have learned before. The limit as n tends to infinity of a to the n is equal to 0 if a is a number between 0 and 1. If a is a positive number or 0, if it is 0 and it is less than 1, then raised to any infinitely large power, the value becomes 0. It is 1 if a is equal to 1 and tends to infinity if a is greater than 1, right? अब यही हम a to the power 2n के लिए extend करेंगे. This will be 0 when 0 is less than or equal to a square is less than 1, which means negative 1 is less than a less than 1, right? It is 1 when a square is equal to 1, which means a is equal to plus minus 1, and it is infinity when a square is greater than 1, which is nothing but a less than minus 1 or a greater than 1, right? So a to the 2n के लिए definition ऐसी दी जाएगी. So now let's look at an application of limits at infinity. Discuss continuity of the function f of x defined by the limit as n tends to infinity of x to the 2n minus 1 over x to the 2n plus 1. Alright, अब हम इस फंक्शन को पीस वाइज फंक्शन की तरह डिफाइन करेंगे जैसे हमने यहाँ लिखा था. It is x raised to 2n, so we will have this classification of the piecewise function. So f of x will be defined by, अगर x to the 2n पहली ब्रांच से हो, इस ब्रांच से हो, x square, x belongs to minus 1 and 1, x raised to 2n tends to 0. So f of x will tend to negative 1 when negative 1 less than x less than 1, right? F of x, we will replace x raised to 2n by 1 when x is equal to plus minus 1. And when we replace x raised to 2n by 1, f of x becomes exactly 0. Lastly, अगर x less than 1 minus 1 है या x greater than 1 है, x raised to 2n tends to infinity. And infinite limit से के algorithm से आपको याद होगा, we divide by the greatest power of limit tending to infinity, and the answer will be the coefficients of the highest power if the degrees are equal. Here, the coefficients are both 1. We will modify this by saying the limit as n tends to infinity of 1 minus 1 over x raised to 2n by 1 plus 1 over x raised to 2n, where x raised to 2n tends to infinity. So this term tends to 0, this term tends to 0. The limit is 1. So it is 1 when x is less than minus 1 and x greater than 1. Right? So that is how we will uh, discuss the value of f of x at different values of x. Now we will check for continuity at all breaking points of this piecewise function, because between any two breaking points, say between minus 1 and 1, the function is a constant function. So we only need to check the values at minus 1 and 1, right? Minus 1 पे देखते हैं. So checking at minus 1, the left hand limit is clearly 1, comes from the third branch of the piecewise function. Because at the left hand limit x will be less than minus 1, and for all x less than minus 1, f of x is exactly 1. The right hand limit uh, at x minus 1, which means x is greater than minus 1, is minus 1. From here we can conclude left hand right hand limit are unequal, and this has the jump type discontinuity, non-removable discontinuity. So it is discontinuous at x equals minus 1. Similarly, we will check for x equals 1, left hand limit will be minus 1, right hand limit will be 1, right? Again, it has the jump type discontinuity, and it is discontinuous at x equals 1. So the fourth subheading under this topic would be functions defined differently for rational and irrational values. क्या ये कंटिन्यूस होते हैं कि नहीं होते जब फंक्शन ऐसे डिफाइन किया जाता है कि हर रैशनल एक्स के लिए एक वैल्यू है और इरैशनल एक्स के लिए दूसरी वैल्यू है? क्या ये फंक्शंस कंटिन्यूस होते हैं? तो अगर हम एग्जांपल देख लें, f of x defined by the value 1 when x is rational and 0 when x is irrational, which is r except all q's. So, in fact, this function is called the Dirichlet function. Just for trivia, so f of x defined by 1 when x is rational and 0 when x is irrational. Let's check the continuity of this function. So, let x equal a when a is rational. Let's check the continuity at a. A is rational. Sorry. All right. So clearly f of a will be 1 since a is rational. Now we need to check the limit, the left hand limit. The left hand limit will be the limit as x tends to the left neighborhood of a, right? Of f of x. Now let's examine this left hand limit. As x tends to the left neighborhood of a, as x is in the left neighborhood of a, it is not guaranteed that the left neighborhood of a has values which are rational or irrational, which means the left neighborhood of a can be defined as f of a minus h. We don't know if a minus h is rational or irrational. Even though a is rational, we don't know about the rationality of a h, so that a minus h could be rational or irrational, which means could be rational or irrational, right? Which means we cannot conclude the value of the left-hand limit. It is not a fixed number. Left-hand limit is not a fixed real. It does not exist. If the limit does not exist, it has a non-removable discontinuity. In fact, this is oscillating between 1 and 0 as x takes on rational, irrational values. So similarly, the right-hand limit also does not exist because we do not know if a plus h is rational or irrational. And this same procedure can be applied when x is irrational. Then the left-hand limit of x equals when a is irrational. Then a minus h may be again rational or irrational. So we cannot find the left hand or right hand limit of f of x at any x belongs to R. If the limits do not exist for any x belongs to R, we say that f of x is discontinuous with the non-removable type of discontinuity for all real x. And it oscillates. It has an oscillatory non-removable type discontinuity, right? Because limits are oscillating between 1 and 0. So f of x is discontinuous at all real numbers. The next subheading under this topic is the continuity of composite functions. So let's discuss the continuity of composite functions. This is the fifth subheading, composite function. Composite function का मतलब होता है one function inside another function. When we write f of g of x, that is in fact a composite function because we have taken the argument of a function to be another function. And it can be extended to n functions. We can write f of g of h of x and so on. How will we determine the continuity of these functions? So let's take an example for this. Let f of x equal 1 upon 1 minus x. G of x to be defined as the composite function f of x, where the function of f of x is f of x itself. So when we write this algebraically, it will be 1 upon 1 minus x, which reduces to x minus 1 upon x, right? So g of x is x minus 1 upon x. When we check the continuity of f of x, we know it's a rational function. It is continuous over its entire domain. Its domain does not include x equals 1 because denominator becomes 0. So it is discontinuous at x equals 1 with a non-removable type of discontinuity. Therefore, f of x should be discontinuous when f of x equals 1. And when is f of x equals 1? This is f of x when x equals to 0. So g of x should be discontinuous when x equals 0. That is when f of x equals 1. Alright, so now let's check the limit as x tends to 1 of g of x. Because f of x is discontinuous at x equals 1, and g of x will be discontinuous wherever f of x is wherever f of x becomes 1, which is x equals 0. Right? So we know that x equals 0 is a point of discontinuity. What about x equals 1? So the limit as x tends to 1 of g of x, we see that this is 0 from this algebraic expression for g of x by direct substitution. However, g of 1, this function is deceiving. This definition of g of x, where x minus 1 over x is being equated to g of x, is actually only valid when x is unequal to 1. Now, try to think why this is only valid when x is unequal to 1. The answer is that its argument is only undefined when x is equal to 1, right? We had a 1 minus x in our denominator. Only after simplification we got this form of g of x. So we cannot say that since we have got this form of g of x, it is suddenly defined at x equals 1. This definition is only valid when x is unequal to 1. G of 1 is not defined, right? Whenever we try to simplify a composite function, we must keep in mind not only the domain of the outer function g of x, but also the domain of every function appearing in the arguments. Like in this function, f of x was appearing in the argument of f of x, right? F of x. F of x was appearing in the argument. When we simplified, we got x minus 1 over x. However, we must not forget that f of x was not defined at x equals 1. So g of x is also not defined at x equals 1. In addition to x equals 0, we have another point of discontinuity, x equals 1. So that is one thing to keep in mind in case of composite functions, that we must not only check points of discontinuity for the entire composite function, but also for all functions appearing in the arguments, which may get hidden once we simplify. So during simplification, in this step in particular, we should have written that as long as x is unequal to 1, because that x escapes the domain of f of x. And since it escapes the domain of f of x, it is also not part of the domain of g of x. And in this case, it is missing point discontinuity. So this is it for lecture 2. It's time. So our next topic will be the intermediate value theorem, which is a very important application of the concept of continuity. And In our next lecture, we will also look at differentiability. Again, we will look at the first principles, definition of differentiability, how to check for differentiability, and various properties. So, for various topics which come under continuity, there isn't much of concept um, in this chapter, in the first half of this chapter. However, continuity, those few concepts can be applied to a plethora of questions. So I would say that for continuity, it's very important to keep doing questions, keep looking at questions, and over time you will realize you're able to do these questions mentally. You don't really need to write anything down. You're able to see where functions are not defined, where it's escaping the domain, where there's like a missing point, isolated point, asymptotic discontinuity, jump discontinuity, oscillating discontinuity. You're able to imagine all these mentally, able to draw the graph mentally. So that will be the goal for continuity, to do more and more questions, and to be able to visualize the whole concept without writing much down. Because this is one of the few chapters in mathematics where you can solve the entire question just by visualizing the function. Yeah, that's all for today. Thank you for paying attention.